So here's a quick video to get you started on our relative age dating and fossils assignment. So here we have the Grand Canyon. It's a great stratigraphic section of the rock layers that occur in the western United States and the North American plate. We have a series of sedimentary rocks stacked up here, and down below we do have some metamorphic and igneous rocks at the base. And here's some pictures of exploring the Grand Canyon. You can do it by boat, by hiking, by horseback. There's also a lodge down at the base of the Grand Canyon called Phantom Ranch, and you can book a room there and stay there as well. And here is the stratigraphic section of the Grand Canyon, and you see down here we have some igneous and some metamorphic rocks, as I said, overlain by various sedimentary rocks. And we'll explore the elements of this as we move through the presentation. So one of the things we can do across space, so we could do it across the Grand Canyon from the north rim to the south rim, or from one end to the other, or even like beyond that into other surrounding states, is we can do a lithologic correlation. So lithologic means rocks, and we can correlate them across space. Another way we can do this is how the picture shows, where we can actually have core samples of sedimentary strata, and we can look at this and correlate across all of those. And notice there's one unit here that's a limestone. When you see that brick pattern, that's a limestone. And we can correlate that across A and B, but it pinches out at C. But that doesn't mean C doesn't belong with all the other ones. We just have one unit that pinches out, has been eroded away in that one area of our correlation. We can also use fossils to tell the ages of rocks. And so a good index fossil is a fossil of an organism that lived geographically widespread around the earth, but for a relatively short time span. That lets us kind of nail down how old that rock layer may be. And you notice in this picture, this is a biostratigraphic correlation. So notice, like, for example, number 6, this fossil, well, this is a shale over on the left-hand side. It's a limestone on the right. So it's not a lithologic correlation. It's actually a biostratigraphic one where we can match up fossils. And similarly to the lithologic correlation, things pinch out here, like this fossil pinches out 5. We don't see it over here in the first column, but we do see it in the right-hand column. All right, so when we look at that stratigraphic section of the Grand Canyon as an example, there are 4 laws that let us figure out what are the youngest rocks and what are the oldest rocks. And these are very, very straightforward laws, but they're incredibly powerful. And geologists use them all the time to discover the ages of rocks, the relative ages of rocks. Next time we meet, we will actually be learning about absolute ages and how we determine the actual age of a rock. But right now, today, we're learning about the relative ages, which ones are older and which ones are younger. All right, so there are 4 laws we're going to talk about today. The first one is the law of original horizontality. So that tells us that as sediments are being deposited, they are always deposited horizontally. We make that assumption. So horizontal deposition of sediments that then turn into sedimentary rocks. Now, if we see sedimentary rocks at an angle, we know they have been tectonically impacted. So they have been tectonically moved somehow into an angular position. The second law is the law of superposition. And this is incredibly obvious, but again, so powerful. It works with fossils as well. The oldest is on the bottom, the youngest is on the top. So as we look at stacked rocks, the oldest one is on the bottom, followed by younger and younger layers. Law of superposition. All right, the third law of cross-cutting relationships. This is incredibly useful. Notice the picture where you have your law of superposition, your older rocks on the bottom, younger rocks on the top, and they are cut by perhaps an igneous intrusion, an igneous rock. Like here is shown a dike that has come through. It's like a long planar geometry of rock that's cut through. Hot lava came in and then cooled. So you can see an actual example of it down to the right. Now that dike, that igneous intrusion, is the youngest rock that we see in this picture. Something cannot cut through something that doesn't exist. So these layered rocks must be older than what cuts through them. Okay, this works also for faults. So if we had a fault that cut through layers of rocks or even igneous intrusions, that fault would be the youngest thing. Something cannot cut through things that don't exist. So all of the things that whatever a fault or an igneous intrusion cuts through must be younger, or rather must be older than it is. That's the law of cross-cutting relationships. The last one is the law of inclusions, and sometimes you'll see some inclusions of an older rock incorporated into a younger rock. Sometimes that can happen in an igneous intrusion, sometimes it can happen in a sedimentary layer. But either way, whatever rock is in the inclusions, not intrusions, but inclusions, is the older rock. So in this case, rock A is older than rock B. All right, now I want to move on to, those are our laws we use to tell the relative ages of rocks. We need to understand one more concept before we move on today, and that is the concept of unconformities. So when we look at a stratigraphic section like this, we're looking at sedimentary rocks. Those were deposited. Those are environments of deposition. We had a depositional environment of some kind in order to get those sediments that then turned into rocks. But if you look outside and you see rocks on campus or around your house, they are actively being eroded, weathered and eroded, as you learned in the last unit. So we also have periods of weathering and erosion. So what do those look like in a stratigraphic section? Well, they look like missing time because that material that used to be there, that rock material, has been weathered and eroded and carried away through erosion and deposited somewhere else, okay, but not here. What we call those missing time or those erosional layers is an unconformity. And we have several of those in the stratigraphic section everywhere, but especially like in the Grand Canyon. You can see there's several unconformities here. Those are erosional surfaces where we are missing time. At that time, that rock was being weathered and eroded. All right, they are shown on stratigraphic sections like this as a bold wavy line. Those are always unconformities. There are three types. Let's go through the three types. The first type is a disconformity, and that's just where you have all sedimentary rocks, flat-lying sedimentary rocks, an erosional surface overlain by more flat-lying sedimentary rocks. That's a disconformity. The second type is an angular unconformity. You have sedimentary rocks that have then been tilted here tectonically, eroded, and then again, time moves on as always, and it becomes a depositional environment again. And we have flat-lying sedimentary rocks deposited on top. And that angular unconformity is right there between the two. Here's an actual example where we have angular sedimentary rocks overlain by flat-lying sedimentary rocks. So all the ones I've talked about so far are all sedimentary rocks. What if we have, like we do in the base of the Grand Canyon, in igneous rocks and some metamorphic rocks? What do we call that? Well, that's called a nonconformity, when we have igneous or metamorphic rocks overlain by flat-lying sedimentary rocks. Okay, that is called a nonconformity. And we have each of these are found here. Here's a nonconformity right here. Metamorphic rocks, those are shown by those wavy lines, overlain by sedimentary rocks. We have an angular unconformity here. We have angled sedimentary rocks overlain by flat-lying sedimentary rocks. And then up above, we have several disconformities where we have flat-lying sedimentary rocks over flat-lying sedimentary rocks. These rocks, or these unconformities, can also shift with time. So you may have a nonconformity here, shifts over space, into an angular unconformity over space again, and you have a disconformity because the things have changed tectonically or depositionally over space. And again, we see that here where in one area of the canyon, you'll have a nonconformity here, and it shifts into a angular unconformity right there. All right, so the last thing I'm going to show you is how do we go back and use those laws that we learned, those 4 laws of original horizontality, superposition, the law of inclusions, and the law of cross-cutting relationships to kind of suss out and figure out the riddle of what is the oldest rocks and what are the youngest rocks. So here again we have E is a metamorphic rock with that squiggly lines and more crosses here. B, that's an igneous intrusion, and you see the contact metamorphism around that igneous intrusion. That's another clue that it's igneous. So the oldest rock here would be E. E had to exist by the law of cross-cutting relationships before B could intrude into it. So E is the oldest. B is the next oldest, but it doesn't intrude into C. So C is then younger. And now by the law of superposition, we know that C comes before D, comes before A. So A is the youngest, D is next, C, B, and E. And always start with the oldest. It's much easier to do this by starting with the oldest rock first and moving your way up through the youngest, thinking about those 4 laws. All right, you are all set. And here is another picture where you can use those laws to get, as things get even more complicated, and figure out the order of oldest to youngest. But you are free now to go do your assignment, and thank you very much.